Okay, hi everyone, good morning. I'm Esma Rezan Karaca. I'm a master's student from Boğaziçi University. Today I'll present our research on integrating ultra-wideband sensor data into BIM environments by utilizing Revit API. This work aims to improve real-time worker safety monitoring on construction sites. Here's what I will cover today. Construction is one of the most hazardous industries due to its dynamic environment. The construction sector is rapidly digitizing with the adoption of BIM IoT sensors, real-time location systems. Despite the digitization efforts using BIM IoT sensors and RTLS, real-time integration between location data and BIM still remains underdeveloped. Our key question is, how can ultra-wideband sensor data be effectively integrated into BIM environments to enable real-time, scalable, and accurate visualization of worker positions on construction sites? We identified major gaps in current RTLS BIM integration. This also real-time situational awareness still lacks. Manual tracking methods, traditional methods, are reactive and still error-prone. BIM and RTLS integration is common in the construction sector, but they are used in fragmented, separated ways. We want to integrate them, and we want to develop a scalable, generalizable, and integrated real-time worker tracking system within the BIM environment to also monitor the visually. Our objectives are to integrate UV sensor data into Revit environments, enable real-time worker tracking, and ensure the sub-decimeter spatial accuracy, and create immersive visualization using Enscape. Let's look at the current landscape. UVB, computer vision, global positioning system, Bluetooth low energy, and radio frequency identification is common use in construction. But global positioning systems fails in the indoor environment. Bluetooth low energy and RFID have limited accuracy and range. Vision-based systems require costly infrastructure, and they may raise privacy concerns. UV gains traction for high accuracy indoor positioning. BIM environments rarely link dynamically with RTLS data, but they still lack the integrations. RTLS and BIM are often used separately, as I mentioned, and coordinate system misalignment is a key technical hurdle. Revit has open API, but it still lacks dynamic object handling. The standard integration across platforms are lacking. Why we choose ultra-wideband? It is nearly accurate in indoor, works despite obstructions or metal interference, comparing to computer vision. No dependency on lighting or visibility like cameras, and real-time updates are feasible. Data is obtained as a local coordinate system which provides integration easily. Our generated framework, we have 4 components. The first one is data collection. We want to collect the data by utilizing UVB anchors and dynamic UVB tags, and we obtain the data as CSV files. And we want to transmit and process those CSV files by utilizing PyRevit. PyRevit enables to connect with the Revit application program interface. And then we want to immerse the visualization by using virtual plugins such as Enscape. This is our system architecture, how we have the framework. We use the Corvo MDAC ultra-wideband sensors. We used Spider as a create the Python scripts. BIM, we created the BIM modeling as in the level of detail 400. This is our steps to create the plugin with the Revit. This is our experimental setup. We tested our framework in a rectangular corridor. As my colleague mentioned, we had 6 subjects walk in the different paths like X and the Y axis. UV tags placed on each participant's knees, waist, shoulders, and head. This is our corridor plan. We calculated the transformation matrix to align UV data with the Revit referential system. There should be 3 or more non-collinear anchor points in both UV and BIM systems to transform the coordinates robustly. This is our transformation matrix. T, R is the rotation matrix, and T is the translation matrix. How we could manage the transformation? We set the level 0 in Revit to correspondent Z, and we use 2 reference planes to establish origin and x-axis. One plane at the anchor origin A1, and one plane along the direction of increasing x toward to A1 to the A2. We generated our Revit model to enable the integration. We use PyRevit and Revit application program interface to import time-stamped UV data from SCSV files. A script updates the position of a generic model human component at 3-second intervals using the function moveElement based on transformed coordinates. To avoid overload, we retained the positions and then deleted them. This balanced visual track continuity and performance. As we can see at the left side, our experimental corridor. We use Enscape for real-time rendering and visualization. It syncs directly with the Revit model, allowing us to observe the moving avatar in a VR-compatible digital twin environment. This enhances spatial awareness and decision-making. Also, Enscape has further BIM coordination features. As a result, we also managed to obtain the data and create a map. This is the movement tracking line we could manage to create. UV track movement lines are compared with the predefined reference paths and achieved validation within the sub-decimeter accuracy. To ensure real-time responsiveness while avoiding system overload, we used 3-second update interval and retained each position for 10 seconds. These updates were synced with Enscape. However, we faced some limitations, such as Revit isn't optimized for high-frequency movement or small distance, such as in millimeters. While plugin starts to work, we faced system freezes after approximately 300 data points. That's why we iteratively decreased the data points. Sensor occlusion caused occasional jumping data visuals. High computational load is limited, especially when tracking multiple workers because of the GPU limitations. Currently supports only we could only manage the local simulation. We couldn't manage to add our data into the cloud server, but we want to do that for our future work. We want to enable the geofencing, define hazard zones in BIM for alerts. We want to get the permission grant to the restricted zones. We want to also enhance the proactive safety management by logging worker exposure in real time based on risk areas. And we also want to add semantic data such as worker fatigue by fusioning wearable sensors. We also want to enhance the combine different sensors such as global positioning system and ultra-wideband, because global positioning system enables to have the data of the outdoor. For conclusion, the framework that had been created achieved feasible integration of UB and Revit by using the plugin PyRevit. Real-time data visualization could be also achieved. We had achieved the sub-decimeter precision. For the future work, we want to enhance our framework for the high complex construction sites also. Thank you for listening.